Imagine a time before time existed. Picture a reality where space itself was confined to an infinitesimally small point. This point, containing all the matter and energy of our universe, was a maelstrom of unimaginable heat and density. It was a realm governed by chaos where the laws of physics as we know them did not apply. This was the state of our universe in the moments before the Big Bang. The very notion of before the Big Bang is a paradox, as time itself is thought to have emerged from the Big Bang. Yet the human mind struggles to grasp the concept of a beginning without a before. This primal chaos, this singularity, is where our journey to understand the universe's transformation from disorder to order begins. From this chaotic soup of energy, our universe in a sudden and dramatic expansion burst forth. The Big Bang was not an explosion like a detonated bomb. Instead, it was an expansion of space itself, an event that continues to this day. In the first fraction of a second, the universe underwent exponential growth, inflating faster than the speed of light. This period, known as inflation, stretched the fabric of space-time, smoothing out irregularities. As the universe expanded, it cooled. This cooling allowed energy to convert into matter and antimatter. Fortunately, a slight asymmetry existed, with more matter than antimatter. This imbalance allowed matter to survive, forming the building blocks of our universe. The early universe was chaotic and energetic. Particles collided at incredible speeds, governed by forces we are only beginning to understand. Yet within this chaos, the seeds of order were being sown. As the universe continued to expand and cool, a crucial transition occurred. The intense heat that had kept matter in a plasma state, where electrons were stripped from atoms, began to subside. Around 380,000 years after the Big Bang, the temperature dropped enough for electrons to be captured by atomic nuclei, forming the first atoms. This event, known as recombination, had a profound effect on the universe. Before recombination, the universe was opaque, like a thick fog, as photons, particles of light, were constantly scattered by free electrons. With the formation of atoms, the fog lifted. Photons were free to travel unimpeded, and the universe became transparent. The afterglow of this transition can still be observed today as the cosmic microwave background radiation, a faint echo of the Big Bang that permeates all of space. This radiation provides a snapshot of the universe as it was in its infancy, offering valuable clues about the conditions present shortly after the Big Bang. With the formation of atoms, gravity began to exert its influence on the universe's structure. Tiny quantum fluctuations in the early universe, amplified by inflation, provided the seeds for matter to clump together. Gravity acted on these denser regions, pulling in more and more matter, gradually forming a web-like structure of filaments and voids. Within these filaments, gravity continued to draw matter together, forming the first stars and galaxies. These early galaxies were smaller and more irregular than the majestic spiral and elliptical galaxies we observe today. Over billions of years, they collided and merged, gradually evolving into the larger and more complex structures we see in the present-day universe. Gravity's relentless pull transformed the universe from a relatively smooth soup of matter into a complex and intricate tapestry of galaxies, stars, and planets. It is the architect of the cosmic web, the scaffolding upon which all structures in the universe are built. Section 5. Dark Matter and Dark Energy, the Unseen Architects. While gravity plays a crucial role in shaping the universe, it is not the only force at work. Astronomers have observed gravitational effects that cannot be explained by visible matter alone. This has led to the hypothesis of dark matter and dark energy, mysterious substances that make up the vast majority of the universe's mass and energy budget. Dark matter, which does not interact with light, is thought to form a halo around galaxies, providing the extra gravity needed to hold them together. Dark energy, on the other hand, is a more enigmatic force that is causing the expansion of the universe to accelerate. The nature of dark matter and dark energy remains one of the greatest mysteries in modern astrophysics. Understanding these elusive entities is crucial to unraveling the evolution and fate of the universe. Section 6. Galaxies, Islands of Order in the Cosmic Sea. Galaxies are vast collections of stars, gas, dust, and dark matter held together by gravity. They are the fundamental building blocks of the large-scale structure of the universe, forming a vast cosmic web of filaments and voids. Within these galactic islands, order arises from the chaotic dance of gravity and matter. Spiral galaxies like our own Milky Way are characterized by their graceful spiral arms, where new stars are born. Elliptical galaxies, on the other hand, are smoother and more rounded, containing older stellar populations. Irregular galaxies, as their name suggests, lack a defined shape, often the result of galactic collisions or interactions. Galaxies are not static entities. They evolve over billions of years, colliding and merging with their neighbors, triggering bursts of star formation and shaping their morphology. These interactions are essential for the ongoing evolution and enrichment of galaxies, leading to the diversity of galactic structures we observe today. Section 7. Stellar Nurseries. The birth of stars. Within galaxies, stars are born in giant clouds of gas and dust known as nebulae. These stellar nurseries are cold and dense, providing the ideal conditions for gravity to overcome the outward pressure of gas and trigger the collapse of these clouds. As a cloud collapses, it heats up, forming a protostar at its center. The protostar continues to accrete material from the surrounding cloud, increasing its mass and temperature. Eventually, the core of the protostar becomes hot and dense enough to ignite nuclear fusion, the process that powers stars. The birth of a star is a violent and chaotic event, often accompanied by powerful stellar winds and jets that sculpt the surrounding nebula. Yet, from this chaos, a new star emerges, a beacon of light and energy in the vast expanse of space. Section 8. The circle of stellar life, from fusion to supernovae. Once a star ignites nuclear fusion, it enters a stable period, fusing hydrogen into helium and releasing energy. The length of this phase depends on the star's mass. Massive stars burn fuel quickly, living short but brilliant lives. Smaller stars, like our Sun, fuse hydrogen for billions of years. As a star nears its end, it runs out of hydrogen fuel. Massive stars explode as supernovae, seeding the interstellar medium with heavy elements. Smaller stars end their lives by forming planetary nebulae, leaving behind a white dwarf. The death of stars is essential for the cycle of stellar birth, death, and rebirth. Section 9. Cosmic Archaeology, Unraveling the Universe's Past. To understand how the universe transformed from chaos to order, astronomers rely on a combination of observations and theoretical models. They use powerful telescopes on Earth and in space to observe distant objects, capturing light that has been traveling through the cosmos for billions of years. By analyzing the light from distant galaxies and quasars, astronomers can probe the early universe, studying the conditions present shortly after the Big Bang. They can also observe the evolution of galaxies over cosmic time, piecing together the history of galaxy formation and evolution. In addition to telescopes, astronomers use computer simulations to model the evolution of the universe, from the Big Bang to the present day. These simulations allow them to test different theories about the universe's origins and evolution, comparing the results of these simulations to actual observations. Section 10. The fate of the universe, expansion, contraction, or something else. The fate of the universe is ultimately determined by the interplay between gravity and dark energy. If gravity were the dominant force, the expansion of the universe would eventually slow down and reverse, leading to a big crunch, a mirror image of the Big Bang. However, observations suggest that the expansion of the universe is not slowing down but accelerating. This acceleration is attributed to dark energy, a mysterious force that counteracts gravity on cosmic scales. If dark energy continues to dominate, the universe will continue to expand forever, becoming increasingly cold and diffuse. Another possibility is that dark energy's influence could change over time, leading to a big rip where the fabric of space-time itself is torn apart. Alternatively, the universe could reach a state of equilibrium, neither expanding nor contracting. Section 11. The universe, a continuous dance between order and chaos. The journey from the chaotic inferno of the Big Bang to the ordered structures we observe today is a testament to the intricate interplay of fundamental forces and the remarkable ability of nature to create complexity from simplicity. The universe is not a static entity, but rather a dynamic system, constantly evolving and changing. While the universe exhibits a remarkable degree of order on cosmic scales, chaos is never far away. Galactic collisions, supernova explosions, and the formation of black holes are just a few examples of the chaotic events that shape the universe's evolution. The universe is a continuous dance between order and chaos, a delicate balance between creation and destruction. As we continue to explore the cosmos and unravel its mysteries, we gain a deeper appreciation for the intricate processes that have shaped our universe and the delicate balance that sustains it.